Now we go to move into another topic that is called reversible reactions. Reversible reactions. Okay. See, before going further into reversible reaction, see, you think that you are with a matchbox, you are burning a paper. You think that you are burning a paper. So let it be this is a paper. So with the matchbox you are burning. So this will completely go into carbon dioxide and maybe some amount of water vapor it shall be forming. Is there any possibility, is there any way you can bring back this carbon dioxide back to paper? Or carbon dioxide and water, you are having ashes. So can you bring back that into paper? Definitely not possible, because once that reaction happens, once paper is burned to form carbon dioxide and vapor, so then nothing can bring it back. It is once it is happened means happened. Okay, so these type of reactions are nothing but irreversible reaction. That means once happened, nothing can bring it back to its original state or previous condition. But that is not the case with all reactions. There are some reactions, we can also call it as reversible reactions. So we are going to see some examples of reversible reactions. See, one common example I can show you is, the copper sulfate. See, copper sulfate, actually you think in this way, this is a bowl that is containing actually copper sulfate. So this is nothing but copper sulfate solution. Copper sulfate solution. Not solution, copper sulfate crystals. You think in this way, we are very well known that this is a blue in color. Okay. So this is when you are heating, what shall be the cause is, okay. So what shall be the cause is actually this copper sulfate crystals, this will changes into white in color. Okay. So do you know the reason? The reason is this copper sulfate is actually hydrated molecule. So this will be changing into, when you are heating this water vapor, actually these are actually water of hydration. So this will go into, this will evaporize. So 5 water molecules it shall be evaporizing. Okay, 5 water molecules it will go. So that these are actually this anhydrous copper sulfate. That means the copper sulfate that is not having any water, that is actually white in color. This hydrated copper sulfate, that is blue in color. This anhydrous copper sulfate, that is actually white in color. Okay, so now you think that this is actually this is white in color. What we can do? Suppose you think in this way, CuSO4, okay, so 5H2O. So this is when you are heating. Okay, this is actually going to become CuSO4 solid plus 5H2O. Okay, so this is actually blue in color, and anhydrous one, that is actually white in color. Okay, so what I can do is I can pour some water. If I pour some water, this white color copper sulfate, again it absorbs water, and the color will be reversing back. Color will changes back to blue color. Again this anhydrous copper sulfate becoming hydrated copper sulfate. Like this is going to have 5H2O molecule. So that again that reaction it completely changes into blue in color. So the blue color can convert into white color, and white color can reverse into blue color. Okay, so this is possible. So these type of reactions are called reversible reaction, because you can make the forward reaction to happen and vice versa. Okay, we need to look a little bit thermodynamically. Endothermic, you have seen this reversible and irreversible reactions, right? So here actually this thing, CuSO4 5H2O. So when you are heating, what shall happen is CuSO4 solid plus this 5H2O, it shall get out. Okay. So when you are pouring water, the reaction will reverse. You can see actually for reversible reaction we put this type of arrow. So forward reaction, backward reaction. Okay. So here one thing, see, when for this reaction, the forward reaction we are heating. So when you are heating, you know that is nothing but endothermic reactions. Endothermic reaction, because you are supplying heat, right? So you should know actually when your reverse reactions are happening. I mean, like this reverse reaction, actually it is actually exothermic reactions, because see, you are taking a cup of copper sulfate, okay, copper sulfate hydrated, copper sulfate hydrated, okay. So you know you are heating. So how much amount of energy actually to make this forward reaction to happen? Okay, how much amount of energy you are supplying? Okay, how much amount of energy? How much amount of energy you are supplying? Okay, when you are putting water actually in the backward reaction. Okay, in the backward reaction, you know when you are putting water, actually you shall be, you know, this changes into, you know, yeah, 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 here actually this is a white, this is actually blue. So when you are putting water, how much amount of energy it has absorbed, that much amount of energy will be releasing out. So the energy changes for a reversible reaction, that is also reversible. Like how much, suppose if we are supplying 20 kilojoule of energy for converting copper sulfate of H2 into CuSO4, the same 20 kilojoule of energy it will be releasing out. Same 20 kilojoule of energy it is releasing out when you are pouring water. Okay. So these type of reactions are, we call it as, okay, and we call it as, you know, reversible and irreversible reactions. Okay, yeah. Uh, so now there can be a question arises, you know, if it is only this reaction what it was showing, or any other reactions also irreversible reactions. See, in fact, you know, there are many reactions that is reversible. You know, one of the common one is, you know, nitrogen in actually it react with hydrogen to form, you know, ammonia. Actually, this is a reversible reactions. Okay, so this is a reversible reactions, and next one is, you know, sulfur dioxide. Again, you know, this is also gaseous, and you know, it forms SO3. Actually, then one more reaction if I am writing, yeah, calcium carbonate, yeah, calcium decomposition of calcium carbonate. See, calcium carbonate, you know, CaCO3. It when you are heating in high temperature, this is going to be CaO plus CO2. Carbon dioxide is a gas. This is a solid. Okay. So here, you know, this reaction actually is sulfur dioxide and its oxidation. This is for you know, sulfuric acid, H2SO4 production. Okay, and this is actually nothing but ammonia production. We call it as there is a industrial step, you know, that is called Haber process. Haber process. Probably if you have time, you know, you can read something about this Haber process and these reactions. In fact, this particular reaction that has revolutionized completely the chemical industry, because you know, this nitrogen actually it is a, you know, you can say N triple bond. So this bond breaking, it requires a lot of amount of energy. It is not at all a easy process. It requires, you know, very much amount of energy. So you need to supply a lot of amount of energy, then only this bond will be breaking and it will be forming compound. Okay, and then actually this calcium carbonate, of course, you know, when it decomposes, it will form lime. Okay, it is going to form lime, and this is also an industrially important reaction. All these reactions, remember that these are all reversible reactions, and you know, as soon as some amount of SO3 is forming, that is started decomposing back to SO2 and O2. Same way, N2 is enough amount of ammonia is forming, you know, that is started to decompose back to nitrogen and hydrogen. And the same way, calcium carbonate, you know, this is also, it is returning back to calcium carbonate. Okay, so these are all actually reversible reactions. There are many industrially significant reversible reactions are there. These are few. You have seen this reaction, right? N2 plus 3H2, that is in equilibrium with the 2NH3, right? So this, you have seen this reaction. So there is one problem with this reaction. Do you know that? See, you think in this way: a closed container, okay, a closed container. So, or like, it is having some opening. Let it be. So, you think in this way. See, uh, some amount of nitrogen and some amount of hydrogen. So you have added. Definitely, it has formed NH3. Once some sufficient amount of NH3 is forming, that started decomposing back to N2 and hydrogen, right? So this is actually this type of reaction, it is called, it is in dynamic equilibrium. That means what you can understand is, say, suppose initially you added 1 mole of nitrogen. So, and it is forming, let it be 0.5 mole of NH3. See, once 0.5 mole of NH3 is forming, okay, then this reaction start to be in equilibrium. Soon, say from here, 0.5 mole of nitrogen has reacted. So here, actually, this is forming 0.5 mole of NH3. So once 0.5 mole of NH3 is forming, that is started decomposing back to, okay, 0.5 mole of nitrogen. Yeah, okay. So here, you have to know one thing. Now hereafter, how much amount of this forward reaction happens also. As soon as the forward reaction happens, it is getting back, decomposes back to 0.5 mole of nitrogen, right? So no further amount of ammonia, no further amount of ammonia shall be forming. Even if you are adding, say like some more amount of nitrogen also, no response, nothing will happen actually. So of course, nitrogen added, some more amount of ammonia will be forming. Still, it is coming back to its decomposes back to nitrogen and hydrogen. Okay. So here a problem is there. Suppose you think that you want to produce some bulk amount of ammonia. So what is the problem here is, once the ammonia is forming, see, ammonia is formed, then no further, once the equilibrium is attained, okay, then no further amount of ammonia will be forming. So like as soon as ammonia forms, it will decompose back. As soon as ammonia forms, it will decompose back. Okay, what is this is a big problem for the many industries, because suppose their intention is to produce some bulk amount of ammonia. What they will do? They don't have any other way. So this ammonia forms. It is getting decomposes back. It is getting decomposes back. We don't have any other way other than so we don't have any other way, right? So only one thing you can do is, there are many challenges. There are many ways. They can produce bulk amount of ammonia, which we will see in subsequent sections. So anyway, this is the problem with the equilibrium process, that is actually dynamic. So if it is in dynamic equilibrium, we have to if it is in dynamic equilibrium, as soon as the product is forming, it is decomposes back to reactant, and no more amount of product it will be forming as far as it is in equilibrium. So there is a best ways, we have to this equilibrium, we have to disturb this equilibrium so that more product will be forming. And this kind of reaction should never attain equilibrium. It should never attain equilibrium. Once this equilibrium is attained, then reactant will be coming, reactant will be forming, reactant will be forming. So this reaction should not have attained an equilibrium reaction. Okay, it should not attain dynamic equilibrium. Okay.